for the invitation and the opportunity to speak here at UC Santa Cruz. I wish it was in person. It's a beautiful campus, but it's fine to be doing it remotely, I suppose. So hope you all are doing well in the COVID world and enjoying this course. I don't know what all you've studied in the course, so I will be talking about deep neural networks at some high level. I won't be going into deep details about the algorithms themselves, because Advait said that you probably will be learning about these things in other courses or maybe in this course as well. And I'll try to keep it high level as far as the deep neural networks methods are concerned, and talk about some applications at LinkedIn for deep neural networks and search and recommendation systems. So I just wanted to sort of start with, what is deep neural networks all about, right? So I think in 2009, 2010 timeframe is when deep neural networks became the new rage, and it became really popular over the several years since then. But I still recall in 2009, the first place where deep neural networks made an impact was in the area of speech recognition, an area that I've been working on for many years. And in 2009, Microsoft came out with a method where they replaced a traditional speech recognition approach with deep neural networks and found that they got a 35% relative improvement over the previous techniques. And that was a mind-boggling sort of win. In previous years, people used to get like just 3% relative improvements, 5% relative improvements. That 5% would be considered huge. But a 35%, I think it was something like that, 35% relative improvement on a pretty hard conversational speech recognition task was really unheard of. And that really, I think, propelled deep neural networks into what it is today. And following that, there were advances made in the area of image processing, image classification. And now in the last 3 years or so, as I would say since 2017, when transformer methods first came into play. Of course, even before that, I should say there were encoder-decoder methods. I would say over the last 5 years or so, deep neural networks have made a big impact in the area of natural language processing as well. And by natural language processing, I would mean text-based natural language processing, because obviously it all started with their application in speech recognition, which is also natural language processing in a sense. Now, deep neural networks isn't really new necessarily. A lot of the techniques in deep neural networks are old. I did my PhD in the early 90s, and rather late 80s, early 90s. And in that time, there was like the first wave of new deep neural network research going on. And a lot of the methods that are used today were invented then: convolutional neural networks, RNNs, and so on and so forth. However, they didn't make so much impact in interesting hard tasks like speech recognition and image processing, because we didn't have as much data and didn't have enough compute power to train the large networks that we train today. In fact, the 2009 example that I gave you with the speech recognition 35% win that Microsoft saw, that was using a method that was actually invented in 1994. I shouldn't say invented, or rather published in 1994 by ICSI at Berkeley and SRI at that time. But at that time, the researchers could not use the sort of neural networks that they were using for speech recognition were fairly shallow. Hundreds of parameters instead of thousands and thousands of parameters, just a few tens of classes instead of thousands of classes. And that alone made this big difference of, not getting any gains over the traditional method to getting a 35% relative improvement. So deep neural network, I think, is here to stay. There have been several new techniques that have come into play as well, and a lot of old wine in a new bottle. But be that as it may, I think it's a very exciting space, and several applications in different areas, including natural language processing. So why doesn't my slide change? Oh, there we go. Okay. So these are the people that I've been working with at LinkedIn who have done all the work as far as the LinkedIn applications for deep neural networks that I'll be talking about. Bo Long is no longer at LinkedIn, but he was there until fairly recently. And so I'll just be presenting the work as far as the LinkedIn work is concerned, but these are the guys and women who did this work. So in terms of an agenda, I will start with talking about how natural language processing is used in search and recommendation systems, because LinkedIn is a professional social network where we are interested in showing content to our professional members. Deep neural networks will follow that. So I'll talk about how we use deep neural networks in natural language processing. And specifically, I will talk about what we call embeddings. These are just ways in which deep neural networks are used to represent words and sentences in natural language. I'll also be talking about the BERT neural network model and transfer learning, and at a high level, that is. And then I will talk about how we use BERT in some real world examples at LinkedIn. I'm not going to be talking about all the examples of deep neural network use cases at LinkedIn, but I will talk about how we use BERT. And I think that's particularly exciting because BERT was published in 2018, a year after the Transformer paper was published. So it's fairly new. And since then, there's been even more progress. But I think it's a good sort of exercise to show how we can use a model such as BERT to make significant improvements in online metrics for LinkedIn applications. So let's talk about how we use natural language processing in search and recommendation, right? So at LinkedIn, we are interested in doing things like recommending people jobs, or also recommending other people to connect, and so forth. So our mission at LinkedIn is to connect the world's professionals to make them more productive and successful, right? So this is a professional social network, and we want to connect people in this manner so that they learn more, they connect with like-minded people more, they maybe learn some courses, they get new jobs, and they advance in their career and become more successful over time. So job recommendations is a big deal at LinkedIn, right? How do we recommend jobs? So if you go to the LinkedIn site and click on this job tab over here, I don't know if you can see my cursor. Is the cursor visible?
Yeah.
Okay, yeah, it's visible. Yeah, right. So there's the job tab there. If you click that, then you're going to be shown a bunch of jobs. And these jobs that you're shown is basically based upon your profile, your LinkedIn profile that you've created, as well as any historical behavior that you've engaged in with at LinkedIn. So the way we would use natural language processing would be like this. So essentially, we want to be able to recommend you jobs, right? So what we do is the member shows up, and what we have access to is the member's profile. And we also know the member's historical behavior in terms of what jobs did the member view, what schools did the member view, what search queries did the member type, how many job searches did the member do, and so forth. We have all the historical behavior that we can also look at what previous jobs the member engaged with, what previous articles the member engaged with. And these previous jobs and articles that the member engaged with are basically text content. So we would do text processing or natural language processing on that text content to develop some sort of understanding of what sort of material this member has engaged with in the past. And the presumption is that whatever you engaged with in the past is the kind of thing that you might be interested in. So that gives us one sort of idea of member understanding is your previous behavior with engaging with different text documents at LinkedIn. The second is your profile itself, right? So every LinkedIn member has a profile, and this profile is basically composed of text. There is some structured aspect to the profile, but there's also unstructured aspect where you can just type in your summary, type in a description of the job that you did in a previous company, and so forth. So using, again, natural language processing, which I'm calling text processing here, we can develop an understanding of the profile as well. Now, speaking a little bit high level over here, when we talk in terms of developing an understanding of the profile, it means we will output some sort of a feature which would sort of represent the machine's understanding of this person's profile. And similarly, we have jobs that we want to show to this user. And the job descriptions and the job title and the job requirements and all of the stuff, which is, again, text, which describing the job, can be processed using natural language processing to develop an understanding of the jobs. And because now we have an understanding of the job and the member, we can sort of put this together to see which job should be recommended to this member. The idea is that the job that is more relevant to this member, who's the job whose a feature or whose description looks similar to this member, is the one that we want to recommend. And that's how we would use natural language processing here for job recommendation. Now, the next thing that one can do is job search, right? So now instead of just showing up on LinkedIn, you might show up at LinkedIn and type in a query, such as computer vision neural network. That's the query that is typed in over here in the job tab. And so we show a bunch of jobs. These are the jobs relevant to this particular search query. And how do we show these jobs to this user? It's very similar to what we just did before. The only difference in this case is that we also now have a query. We have the user's profile. I haven't shown the user's behavioral history, but that is also available to us, just like when we were doing recommendation. But we also have this raw query that the user has typed. So what we do is typically in a search application, we will first retrieve a bunch of documents or jobs in this case that we think might be relevant for this member. And in the retrieval phase, we typically use a simple, cheaper model to retrieve a whole bunch of documents that might make sense. And then after that, we have a ranking phase where the retrieved documents, so we initially have a huge number of jobs, thousands and thousands of jobs. We might retrieve a few hundred, and then we would rank them to show the user a few tens of jobs, right? So the ranking model's task is to take the retrieved documents, in this case, the jobs, and use a more complex model, which has got more power, to rank those jobs in accordance of their relevance to the query and the member's profile. So we have the raw query. So how do we process this? We will first reformulate the query to write the query in multiple different ways using AI, right? So one technique that natural language processing can be used for over here is to take a query and create similar queries, right? Take a query like machine learning for computer vision, and maybe add similar queries like convolutional networks for computer vision or something like that. I'm just making this up, but you could imagine different sort of queries that might be relevant for a person looking for a job in computer vision applying machine learning. And the idea of this query reformulation is to write your original query in different ways so that the retrieval phase allows us to retrieve many more jobs that are possibly relevant to this query. After that, we will go ahead and do query understanding in a very similar way that we talked about before. We will use AI, artificial intelligence models like neural networks to apply natural language processing on the query to develop some understanding of the query. Now that we have the queries, we have understand the query and the member's profile, and we also have these various job descriptions that are ones that we can show to this user, we will see which job matches to this user in query and rank them accordingly. So this is in general how NLP is used in search and recommendation systems. So at LinkedIn, this is the way we think of deep NLP. This is the way we sort of conceptualize deep natural language processing or deep neural networks for NLP at LinkedIn. At the bottom, we have what we call representational learning. And I'll go into a little bit later about what this means. Basically, the idea of representation learning is to develop models that can take the input text and form some sort of a fixed dimensional representation of this text. So text can be any length. You can have a sentence of 3 words or of 10 words. It can be a whole paragraph and so forth. But if we want to compare a query and a paragraph, it's not very easy because the query is of length 5, maybe the paragraph might be of length 100. How do we compare these two things? We can think in terms of comparing two things in a fixed dimensional, in an n-dimensional space. And so what we do is we convert these text into a fixed dimensional representation, often called a dense vector. You might have heard the term dense vector, which just means a real valued vector in a fixed dimensional n-dimensional space. where each component of the vector, has some sort of has some real value. So the representational learning is all about taking the input text and converting it into a fixed dimensional vector, a dense vector, maybe a 100-dimensional vector, 512-dimensional vector, whatever. Okay. Now, then we think in terms of this vector as a feature, as a representation of the input text, and then we want to model this input text in different ways. So the input text might be a sequence of words, and each word may be converted into a fixed dimensional representation, or the entire sentence may be converted into a fixed dimensional representation. And there's various different things that can happen. So we are talking very high level over here. So when we think about representational learning, just assume that what's coming out of the representational learning box is that what's going into the representational learning is a sequence of words comprising a sentence or a paragraph, let's say. And what's coming out is a fixed dimensional representation for the entire sentence, as well as possibly a fixed dimensional representation for each word in that sentence. So you can then take this and do some sort of sequential modeling, which is the main neural network engine that we will be using here at LinkedIn. The sequential modeling can do one of, we've shown here 5 different tasks. And for example, we can do sequential tagging. We can take the input sequence of feature vector representations of the words and tag them. Tagging is the task of, for example, you have a sentence and you want to tag each word into its part of speech. Or in our case, what we want to do is we want to tell, is the word a first name? Is it a last name? Is the word in the query a company name? And things like that. Because if it's a first name, last name, then we know that maybe the person is searching for people. If it's a company name, we think maybe the person is looking for a job. I mean, there could be different ways we use this, but we would do tagging as one possible application of deep neural networks. Another application is classification. So the query that comes in, we may want to decide whether this query, and this is actually one of the applications I will be talking about. We may want to know if this query is a people search query, is it a job search query, is it a company search query, is it a LinkedIn learning query? And we want to know that so that we can show the right results to this user. So in this case, what's happening is we will take the representation of the whole input query, that is the whole sentence as opposed to the words, and we will take that representation and try to figure out and input that into another neural network model to decide what class this query falls into. So this is a classification task. The third one on top here is a matching task. So the idea here is we have documents and we want to be able to rank these documents in accordance to their relevance to an input query or to an input profile. And so now the model, the neural network that we will use here is a model that will apply a score, that will give a score to each of these documents in relation to the input user and query. And the idea is we would then rank these documents according to those scores. On the right side, we have a couple of natural language generation tasks. So the first is query expansion. We already talked about this before, right? You're given an input query and you might want to expand it into other queries so that this retrieval phase of search can retrieve more documents. Another use case is today, if you go to LinkedIn and type a query, we'll show you a bunch of search results. And under those search results, we'll show you other queries that might be relevant as well. So you could just click those queries and get even more search results. So that's how we use this. And we are using an encoder-decoder with attention model. I don't know if you know about those models, but it's another deep neural network model that's been very powerful in the area of things like machine translation and so forth. We're using it for expanding queries into other queries that the user can use. And finally, we have sequence completion. This is the case where you start typing a query and you want the system to complete the query for you, so that rather than finishing the entire query, you can actually just click the query, one of the queries that the system offers, and do your search that way. And for this, we are using a deep neural network language model to do this task. So these are the various tasks we're doing. Today, I will be talking about applications of BERT for natural language, for classification here, and for document ranking. So now let's talk a little bit about deep neural networks and embeddings. I don't know if you have, if you know all this, then maybe you should tell me, and I can go over it faster. But I'll let you tell me as I'm speaking. Feel free to, by the way, feel free to ask questions during the talk as well as after the talk. Since it's we have 1.5 hours, I think we can absolutely talk about stuff during the talk as well. Okay. So at the base, yeah. Is there a question?
Sorry to interrupt. Just give you context. We just did review one-hot text representation.
I'm sorry, I couldn't hear that at all.
We did just go over one-hot text representation.
Otherwise, could you repeat that? I couldn't hear it.
I think he said that we just went over one hot encoding representation.
Yeah.
Okay, good. All right. So,
Yeah.
So the one hot representation is this, right? So what we're talking about here is we want to be able to represent the atoms of natural language. And if we pretend that the atom, the basic unit of natural language, is a word, then the way we would represent this is, just really quickly, if you have 100,000 vocabulary in your application, then only those 100,000 words would be allowable in your model. Anything else would not be allowed. And we would simply represent each word with a 1 in the position of that vocabulary corresponding to that word and a 0 everywhere else. Now, the main problems with this approach is two. One is, of course, it's a very sparse representation. You have a 100,000 dimensional vector to represent each word, which is probably very wasteful. Zeros everywhere and a 1 in only one place. But the other important aspect also is that you can't really do much with this, right? So we know that the word mouse and the word rat are very similar words. They're semantically the same thing. Not same thing, but very similar. And cow and buffalo are also similar because they are both a different sort of animal. They're bovine animals. The first two are rodents. And these two sets of animals don't resemble each other at all. However, if you look at a one-hot representation, the distance between any two one-hot representations will be identical. So the distance between mouse and rat and between mouse and cow is the same, but that is not what we want. So what we're going to do is we want to be able to think in terms of dense representations where such semantic similarities or differences are apparent in the representation itself. So to do this, we use deep neural networks. And to deep neural network, again, from the standpoint of this slide, just think about it as a model which has many layers. Each layer has a bunch of neurons. And don't worry about exactly how these neurons are connected or the structure of this model, but just think in terms of each layer of the network being able to take the output of the previous layer and produce a fixed dimensional, real valued vector as its output. So the dense representation. So each of these layers is going to produce a dense representation on its output. It's going to feed it to the next layer, which will produce another dense representation, and so on till we reach the final output of the neural network. Now, typically neural networks are going to do some sort of classification task or something like that. So the final layer may not be an embedding, it might be an output like 1 or 0. Is this a dog or is it a cat? That kind of thing, right? So let's pretend that we are looking at the embedding after any of these layers. Now I'm showing the first layer output, right? So the input is the word mouse. We have the one-hot representation. And in this embedding space, the word mouse might be this dot in this 100-dimensional space over here. Now the word rat, we would like it to be close to the word mouse in this 100-dimensional embedding space, even though it is equally close to the word rat as the word cow is in the 100,000 dimensional vocabulary space. Now the word cow in this smaller 100-dimensional space, we would want it to be far away from rat and mouse because it's not semantically the same thing. And the word buffalo, we would like it to be closer to cow than it is to rat and mouse. But we would like the distance between cow and buffalo to perhaps be more than the distance between rat and mouse because cows and buffaloes are not as similar as rats and mice. Okay, so this is kind of what we might want from a neural network feature representation of these words. So this is what we would call embeddings, representations, dense vectors, all interchangeable words. Is that clear? All right, so now in terms of how these embeddings are computed, I'm not going to go into details of this, but there have been different techniques that people have come up with in the past. They all have to do with taking a whole bunch of natural language data and using those data to train a neural network model in a sort of unsupervised way, because you don't provide it explicit labels, but you use the text itself to learn things. For example, you might take a sequence of words and make the neural network predict the middle word or the word in question based upon the surrounding words. Or you might take the word in question and try to predict the other words in the sentence. So techniques like this are used in word-to-vec, for example, to form representations of that word in question. Now, these are called static embeddings. They are static because irrespective of which context the word is used in, we will get the same exact dense vector representation for that word. So let's take the word horse. It's an animal that eats grass and looks something like a cow, is not, I mean, closer to a cow than a rat. But this animal would have some representation, and in the word-to-vec approach, it'll be fixed and that's it. The word HORSE has this one representation. However, in contextual embeddings, we would like the words to have different representations depending upon the context in which they occur. So the same word horse can have a completely different meaning in the sentence, the horse ate grass, where obviously we're referring to this animal. Whereas the word don't horse around means a verb where horsing around means to, act funny and to fool around, right? So a horse in the second sentence is a verb which means fooling around. And in the first case, it's an animal, which we all know. And clearly these two words ought to have completely different representations because they don't mean anything like each other. But in a static representation, they would. There would be only one fixed dimensional representation for this. So techniques like BERT enable us to take an input word in the context of other words in which they appear and give different representations for the same word. So if we said the horse was horsing around, then the first horse and the second horse would have different representations. So now let's talk about neural networks and embeddings and talk in terms of the bigger picture. Once we have these embeddings from the neural network, we want to do something with it. It's not enough to just have an embedding or a fixed dimensional representation for each word or each sentence. We want to do something with it. And these are the 5 tasks that I talked about before. Remember this, the sequence tagging task, the classification task, the document tracking task, the query completion task, and so forth. So we have different tasks that one might want to do. So in this picture, this pictorial over here, I'm thinking of the first 3 layers of this neural network as taking the input text and producing an embedding for each of the words or maybe for the whole sentence. But we produce embeddings at this layer where we have the dotted lines. And the layer on top of that is doing some kind of inference. In other words, it's taking the sentence and maybe trying to classify it as a spam sentence or a not spam sentence, or maybe as a happy sentence or a sad sentence. Or maybe we're trying to do some sort of tagging of each of the words of the sentence into different classes, into different categories for each of the words. So that's the inference part. So typically we're always doing, any machine learning application has 2 parts. One is the feature extraction part, which I'm calling here the embedding computation. And the second is the inference part, which takes the features and does some sort of inference on top of it. Now, where does embedding end and inference start? It really could be anywhere. You could think of the embedding being the input one hot dimensional, word representation, and the entire neural network being an inference engine. Or you could think of the first layer being the feature and the rest of it being the inference engine, and so on and so forth. And really, there is no one way to look at this, but it's all application specific. Depending upon the application, it becomes kind of obvious the way you're using a neural network, which part of it you're thinking of more of like an inference engine, and which part you're thinking of more as like a feature extraction or embedding computation engine.
I have a question.
Yeah.
In the embedding process, is there any use cases where we need to use the static against the contextual? like in the real world example, like is there is any preferences between both?
So there is no, if you had your choice, you would always use a more powerful representation, which would be the contextual one, right? Because the contextual representation is clearly going to give you more allow you to distinguish better between words because you have the contextual meaning of the word. The reason to prefer one over the other would be computational. Sometimes the contextual representations like BERT may be far more computationally inefficient than a technique that is static, where you can just look up the representation from a pre-computed set, right? Because you can always just pre-compute these representations for the words and use a lookup to find the representation for the word. Whereas for BERT, because you don't know the context of the word till you actually see it, you're forced to compute it online. And so that could be one of the big differences between contextual representations and static representations. The contextual representations have to be computed online, unless it's for something like a job description, which is fixed. And so you could pre-compute those. But a query which you're typing in, you don't know what it is till the person actually types it. And so that has to be computed online as opposed to static representations. It will give you better power all the time. Does that answer the question?
Okay, yeah. Just a follow-up question. How often we have the limitation of computation in the big, I could imagine like big companies have resources for it. So how often we have the limitation of resources, like in terms of computation in the real world?
Oh, all the time. For example, BERT has, the smaller BERT that Google released has 100 million parameters. The larger one has 350 million parameters. And now people are coming up with models with billions of parameters. There's no way that we would be able to run a billion parameter language model to process queries in real time at LinkedIn right now, not at other companies, right? So there is always going to be this issue of using the most powerful and best model in real time using the available compute that you have. So this is always an issue because people are coming up with better and better ways of doing modeling and representation that is more powerful and that have more accurate performance. And compute always falls back, and it's always a game of catch up there.
Okay, thank you.
So coming back to the representation versus inference, I'm going to be talking about BERT, as I said. So this is just a pictorial to show that BERT is, if we have this BERT model here, the BERT model can be thought of as taking the input sequence of words and computing a representation, which is the embedding below this dashed line. And after the dashed line, we have some sort of classification network that can decide if the input sentence is spam or not spam. I took this picture from Jay Alamar's blog, post, Medium post, I think. It's actually, if you haven't ever seen Jay Alamar's posts, I actually recommend them. He does a pretty good job of pictorially explaining these complex models like BERT and transformers and so forth. So this picture on the left is taken from his post. Okay, so now I'm going to talk about BERT itself because we're going to be using it in our 2 applications at LinkedIn that I'll be talking about. But I'm going to talk about this at a really high level, okay? So think of a model. This is a neural network model, obviously, because we have multiple layers, and each layer has multiple nodes, which I'm labeling here as TRM. TRM stands for transformer. So BERT is a transformer-based model. And so first we will talk about what is a transformer-based model. After that, we will talk about BERT, and then I'll talk about the use cases. So in a transformer model, we have an input sequence of words, W1 through Wn, but it's a fixed length. So the length of the input is fixed. And then if your sentence is longer than this, then you might just cut it short. If it's shorter, you can pad it, right? So either way, you're going to have a fixed length sentence over here as an input. Each of these words is then converted to some sort of a embedding at the first layer of this model. And this embedding is simply going to take this one hot representation at the W1, W2 level, converting it to some maybe 500 dimensional hidden vector, hidden representation, or an embedding representation, which is this dense representation that we talked about. And after that, we have this multiple layer of transformers. So now we need to know what a transformer looks like, because a transformer is the basic unit here in this network. So this is where we will look at the, so here I'm just blowing up this transformer. A transformer is composed of two components. The second component on the top here is a multi-layer perceptron. So this is your standard feed-forward neural network with multiple neurons in each layer and multiple layers, okay? And the first layer of the transformer is what is called a self-attention layer. Now the self-attention layer does the following. Well, what we're trying to do, remember, is to represent each of these words, form a representation for each of these input words. So over here, we are looking at the word corresponding to WN, right? So the output of this transformer should be a fixed dimensional, let's say a 100-dimensional vector, which represents the word WN, okay? Now, we want this to be contextual. So the way this is contextual is because this transformer is not only getting input from this word WN through this straight line path, but it's also getting input from every other word in the sentence. And similarly, the word W2 gets input from the W2 path, but also every other word in the sentence, both from the left and from the right, right? So it is not a left-right model. We're actually seeing words from both sides. Now, what the self-attention layer does is the following. We want to sort of decide how much weight to assign to each of these other words for this word over here, for WN. And similarly for W2, we want to decide how much weight to assign to each of these other words when we are representing W2. And the weight that we will assign to each of these other words will sum to 1. So it'll be like think of it as a probability of this word, what is the probability that this word is meaningful to W2, that W2 itself is meaningful to W2, and WN is meaningful to W2. What are these different probabilities? We'll have this for each of these words, W1, W2 through WN at this layer. Those probabilities are computed by the self-attention mechanism. It's called self-attention because we are trying to take each word and trying to figure out which of the other words in the same sentence, in other words, the self sentence, right? All the words in the sentence are attending to all the other words in the sentence to figure out how important these other words are to this word in question. And typically the way this is done is we will take the word, supposing the word WN, and we will try to see how similar this word is in some mechanism, such as a dot product or something like that, to the other words in the sentence. And the words that for which the dot product value is high, in other words, the distance between these words is small, for those words, we would give a higher weight. And for the words where the distance is very small, we would give a lower weight. And the self-attention mechanism is a little neural network that does that. And the output of this is going to be simply a weight value that sums to 1 across all these n words. Then what we do is whatever is the representation that has been computed for these words in this previous layer. And there is also some further transformations we do to that, but that is not very important for the purpose of this discussion. We can think of it as these words all having some sort of an embedding representation or dense vector representation. But the dense vector representation for this word at this WN at this layer is going to be the weighted sum of the dense vector representations of all the words in the sentence at the previous layer, modulo some small transformation, which I'm not going to go into, okay? So that is what self-attention does. And so you can imagine that by doing this, if this was the word horse, it would have a different representation depending upon which were the other words in the sentence. Because if we didn't have these other paths, these cross connections, and only had the straight path, then obviously we would not be able to get any sort of contextual representation. But these cross connection paths give you that contextual representation. Now in a transform, so that's a transformer. This is what a transformer is made of. We then take that representation from self-attention and pass it through a multi-layer perceptron to get a final transformation. That's simply how the transformer works. Now, could they have done something else? Yes, they could have done many other things, but they chose to use this specific structure, and it tends to work very well, right? Then the transformer network is simply a bunch of transformers in every layer and a whole lot of layers of these transformers. And the more the layers you have, the deeper the network, and the more it becomes a deep neural network. So typically we'll have 9, 12, 24 layers of these transformers. BERT, for example, the one that Google released, has a 12-layer transformer, a 12-layer BERT model, and also a 24-layer BERT model, where each of these hidden representations is a 768-dimensional hidden representation. And there are other complexities having to do with self-attention as well. But it's a fairly complicated model, which at the end of the 24th layer or the 12th layer will give you the representation of the word horse that was input over here. So at each layer, we're doing the self-attention, figuring out how these other words impact the current word. And we're doing it layer by layer by layer. And as we build up all these layers, we get more and more representational power and better performance. And all that is just empirical. How many layers do you need? How many dimensional representation do you need? All that is an empirical thing. Now, what is BERT? So BERT is simply a transformer model. So remember the previous slide showed you the transformer model. Whoops, the previous slide here shows you what a transformer model looks like. And the next slide here is the same thing, right? So BERT is essentially a transformer model. The difference is how it is trained. The initial transformer paper in 2017 actually had an encoder model for the transformer, and they had a decoder model as well. So the encoder model would take the input words and come up with a set of representations for each of the input words at the output of the encoder transformer. Each of these T1, T2, Tn would be a 500-dimensional vector, for example, right? And then the decoder transformer in that paper, I think they were doing a machine translation task. They would take the sequence of encoder outputs, and the decoder transformer would try to translate that into some other language. So the output of the decoder would be words in the other language. The input of the decoder would be these embeddings from the encoder. So they had these two different transformer models. Now BERT ignores the decoder transformer and only uses the encoder transformer. So that's one thing. The second thing is BERT is a neural network for natural language processing model that is exploiting something called transfer learning. So transfer learning is a significant component of BERT. We'll talk about that. And it involves two components, two phases. The first phase is what is called pre-training, and the second phase is what is called fine-tuning. And we will maybe show in the next slide what this means, right? So BERT is, what is it from a structure standpoint, from an architecture standpoint? It is just a transformer model that we've already seen before. That was published in 2017. But what BERT does with that is says, hey, let's take this transformer model and do something smart with it. So what they do is they train the transformer model in a specific way in a phase called pre-training, which enables this model to create representations, contextual representations for each word, as well as a representation for the entire sentence. So it does two things. It'll produce a representation for the entire sentence, as well as a representation for each of the words in the sentence. And it does this by simply munging over a huge corpus of data. In particular, they use the Wikipedia corpus and a corpus called the books corpus. That's what Google used to train BERT, comprised of 3.3 billion words in total. And they trained BERT in an unsupervised manner. I'll state what I mean by unsupervised. It's not exactly unsupervised, but no human has produced any sort of labels for each of these words in the Wikipedia corpus. They just take Wikipedia and do something with it, but they create some tasks internally which provide them that supervision. And so they kind of do this self-learning, so to speak, in this pre-training phase. You can think of pre-training from a human analogy as we all, when we were born, we didn't know anything. We didn't know any language. And then we were exposed to language slowly and slowly. We first learned some rhymes, and we learned something more complex. We then studied technology. In our case, we studied books. We read blogs. We did all this stuff. And over time, we kind of got exposed to a whole bunch of text. Nobody necessarily gave us labels. I mean, sometimes we would get labels as well, but a lot of the time we don't. Like when we're reading a book, there's no labels there. We're just reading, right? So when we read books and stuff, we form an understanding in our head of what these words mean. And our own neural network in our brain sort of gets a representation for these words merely by being exposed and reading all this text. That's what the pre-training part of BERT is doing. In the fine-tuning phase, what we're saying is, hey, now we have this brain, this neural network that kind of is able to represent words and sentences in intelligent, semantically meaningful ways. What can we do with this? Well, we could then do some sort of tasks. For example, we can do a classification task. We can say, is this sentence a happy or a sad sentence? Is it a people search query or a job search query? Is this word a first name? Is it a company name? And things like that. So these are the fine-tuning actual applications that we're interested in. And from a human perspective, what might these mean? For example, maybe there's different types of poetry, right? Maybe couplets, maybe rhymes, maybe things that don't rhyme, limericks. And by reading, if you don't know these things, and all of this maybe just looks like poetry. But if somebody says, hey, these are limericks and these are like other sort of rhymes, maybe you will be able to say, okay, I can now understand how I can distinguish between a limerick and something else. And that doesn't take much effort. If you have already formed a good representation of language in your head through this pre-training phase, it doesn't take that much learning to be able to do the fine-tuning tasks. In this case, the poetry example that I give you for humans. In the case of machines, it would be the kind of classification tasks that I talked about. So typically what happens is in pre-training, we use a huge corpus of data and in an unsupervised way, learn the BERT model so that it can form representations. And then in fine-tuning, we add one layer on top of BERT, a very simple neural network on top of the last layer of BERT where the embeddings are formed in order to do the fine-tuning task. And fine-tuning can typically be done with a much smaller amount of data. So tens of thousands of utterances, sentences, as opposed to hundreds of or millions of sentences that we would use in pre-training. Okay, so now let me talk specifically about how BERT does pre-training. So again, this big rectangle here is just a transformer model. It's the same BERT that we had in the previous slide. This whole thing is a transformer model. The input to the transformer model is the sequence of words, and the output of the transformer model is going to be an embedding for each of the words in the input. So to that extent, it's exactly the same. But now BERT thinks of this in slightly different ways. It says the first input to BERT is not a word. Instead, it's simply called the CLS token. This token, in a way, represents the entire sentence that BERT is looking at. That's number one. Number two, because of the way they do pre-training, BERT has two input sentences coming in. Sentence number one, on here on the left, followed by a separation token, followed by sentence number two. And the reason we have two sentences is because of the way BERT has decided to do, or the people who invented BERT decided to do pre-training, right? So the pre-training in BERT is done using two tasks. The first task is trying to predict any random word that gets masked. So we will take the input sentence, randomly mask 10% of the input sentence. So let's say this word was masked. And the job of BERT in the pre-training phase is to predict that sentence, that word. So for example, if the first sentence was, the horse ate grass, right? Then I mask the word horse, and so I have the blank ate grass. And BERT's task in the pre-training phase is to be able to predict horse. Does that make sense? So imagine that you didn't know any language, you're a baby, you have no language, you have not been exposed to language at all. And now you're given a sentence, the horse ate grass, but you're shown the blank ate grass, and you're trying to predict the horse ate grass. Some other example, you might actually see the horse ate blank, and grass was the thing you're supposed to predict. So you have some exposure to this. But the point is that the horse ate grass, the cow ate grass, the buffalo ate grass, the deer ate grass. All of these animals eat grass. And if this model learns to predict horse, deer, buffalo, because all of these things would be in the input corpora. it's not that it only sees the horse ate grass. It would see other sentences like the cow ate grass as well, or maybe the deer ate grass also. So you'll see all these sentences. And over time, what it will learn by being exposed to this and being asked to predict this word would be a representation here. That is W2, the output is the representation, the dense vector representation, where the words cow, horse, deer will all get very similar representations. If all we saw was the cow ate grass, the buffalo ate grass, the deer ate grass, and those words cow, buffalo, and deer appeared in no other context except this one fixed exact same context, then the representation for those words would be identical. Because as far as this model is concerned, cow, buffalo, and deer are identical because we never see them in any other context except the blank ate grass. But of course, we would see deer in other contexts, like the tiger ate the deer, or and stuff like that. And so we would be able to distinguish deer from cow and buffalo for other reasons. So that is one task that BERT is trying to do in pre-training. The point I'm making here is merely by being exposed to all this language, BERT is forming some sort of a representation of these words by doing this internal learning by itself, trying to predict these masked words. The next task that BERT is doing is to predict the next sentence. So imagine that you have a sequence of sentences in a paragraph. You would imagine that sentence number 2 is somewhat similar to sentence, it follows sentence number 1 in some semantic way. And so we should be able to tell if sentence number 2 sort of is a meaningful next sentence for sentence number 1. Whereas sentence number N or some other sentence in a completely different paragraph may not have any semantic meaning to sentence number 1 and may not really follow it at all in any meaningful way. So BERT tries to predict this. Given all this input corpora, the wiki corpus and the books corpus, one of the tasks in BERT is to take a sentence and either, so we will give it during training 2 types of cases. One case was where the next sentence, sentence number 2, would be the actual sentence that followed sentence number 1. And the other case, we would randomly pick another situation where sentence number 2 would just be a randomly chosen sentence, which did not necessarily follow sentence number 1. In the first case, we would want the output of this neural network. So what we do is we have this CLS token over here. We add one layer on top of the CLS token. So the CLS embedding is like, let's say a 768 dimensional embedding in the Google BERT case. We add one hidden layer on top of it and predict one output, 0 or 1. 1 for when the next sentence was actually the next sentence for sentence number 1, and 0 for when sentence number 2 was not the next sentence. So that's what this guy is predicting. So now we have this entire BERT model with all its self-attention and multi-layer perceptrons and all these layers and so forth, where we're trying to learn these contextual embeddings to do 2 things. One is to predict a masked word, and the other is to predict if the next sentence follows the previous sentence. So from a language standpoint, we are trying to learn language. We're reading books and we're trying to say, okay, does this sentence follow this? What is this? Can I predict a word given the context of the word and so forth? And they found that by doing these 2 tasks, they can actually form a very good representation of these words so that when they fine tune BERT for other tasks like classification, tagging, entailment, and so on and so forth, they found that in all these tasks, BERT gave a significant and dramatic win over previous techniques. So that's how BERT came to being. And we use it, and Google and Microsoft have actually started using BERT sometime in the end of 2019 for their search engine. And we are also using it now at LinkedIn. So here's a case of how BERT would be used in a fine-tuning classification task. Again, we have the BERT model. The input can be a sentence. Even though we train it with pairs of sentences, you can just as well give it an input sentence because it's just a bunch of words and it's going to give you a representation for each of the words. As I said, we'll also get a representation for the CLS token, which is a representation of the entire sentence. So in a classification task, we would ignore the representations at the output for all these words. The contextual representation of these words is ignored. And we simply take the representation of the sentence, apply one more hidden layer to get a classification neural network. So the output of this neural network is supposed to predict if the input sentence was a spam sentence or a not spam sentence. And we could then train this classification layer along with the entire BERT layer, parameters, using a small amount of classification data corresponding to sentences that are manually marked as spam or not spam. So this is called fine tuning, because not only do we train this one layer over here, we also start off with the weights that we had for the BERT model and learn, fine tune those weights using the task at hand. All right, is that clear? Because now I'm going to be talking about how we use BERT at LinkedIn.
So I have a quick question about the output. So output of the BERT. So because you have two tasks, and then it does like sequence. For the first task, is that a sequence prediction, or how that works? Because you have, for each timestamp, you feed one token, and then like for the empty, for the empty slot.
So in this slide, we have two sentences in pre-training, right? So each sentence is a sequence of words. And as I said, what BERT is trying to do in pre-training is do two tasks. The first task is simply to predict some word that we mask randomly. So if the input sentence is the horse ate grass, I might choose to mask the word horse, or I might choose to mask the word grass. And depending upon which word I've masked, the output of the network is supposed to predict that word. So I'm not doing, it is sequential because we do have we do have an idea of which word in the sentence these, grass and horse are. So we do have a positional encoding as well for BERT, but we are trying to predict what this masked word is. And we are trying to predict whether the next sentence was sentence number 2 was the next sentence or not. We're not trying to predict the next words in the sentence. We're trying to predict a given word. We're trying to predict a word given the surrounding context of the other words.
Right. So in your example, the T2 is where the max words is. So what happened to like T1, T3, T4? Is that time step or?
No, so what will happen is when we give it a specific training example, let's say the specific training example was this example that I'm showing in this picture, right? So now for this example, BERT will produce an output for T1 as well. BERT will produce a W1, a W3, a W4. It will produce outputs for all these words. But during training, we are going to ignore all these words and only try to determine if the W2 was correct. So we're trying to predict the word, the masked input word, which was the word horse, right? So this is the word that the label, the supervision is going to come in only on this word, but not on the words that were not masked.
Okay, I see. Thank you.
But of course, for another example, we might have masked another word. For the same exact sentence, which might repeat some other place in the corpus, we might mask the other word and the supervision would come in for that word. Okay, so let's look at some real world examples of how we use BERT at LinkedIn. And this is nice because, obviously we want to try to use state-of-the-art technology, but sometimes they don't necessarily work in real applications, but this actually does, and it's pretty cool. So first of all, we needed to have some sort of a mechanism to do fine-tuning for document ranking. Google had already released techniques to do fine-tuning for classification, for tagging and other tasks, but not for document ranking. And so we came up with a method to do fine-tuning for document ranking at LinkedIn. It's fairly straightforward and it works as follows. So imagine the task is to rank a bunch of documents D1 through DN for a given query queue. So what we do here is we assume we have a BERT model, right? I say CNN/BERT because we tried both CNN, that is convolutional neural networks, and BERT, but pretend that we have a BERT model instead. So just think of this as BERT, not CNN or BERT, right? Now the query, we have these pairs, QD1, QD2 through QDN. And these are the N documents that we want to rank for this query. So for each of these pairs, QD1, QD2 through QDN, we're going to process the query using BERT. And we are going to process the document also using BERT. So we will have the same BERT model processing Q and D1. And the same BERT model also processes D2, D3, D4 till Dn. The output of the BERT model will be the CLS token that we talked about before. In other words, the representation for the entire query. We are again not interested in the contextual word representations for this task. And for the document, it would be the representation for the entire document. Now, it turns out when we think about documents, we don't think of the document as a whole. We actually think of the document as different fields. So in the application I'll be talking about, we actually had multiple fields of this document. Each field of the document, let's say the document's title, the document's summary, and so forth, could be different fields. Each field of the document is processed through BERT, and each of those fields would get a separate representation with this BERT model. So D1 might have 2 different document representations for 2 different fields of the document, and 1 representation for the query. Okay, so let's pretend like we have the first field of the document and the query, and we have the BERT representation for the query. We have the BERT representation for 1 field of the document. Then if these 2 representations are similar in this space, we would imagine that this document is probably a good match for this query and show it for this query. So we do one thing we can do is we can do a dot product of these 2 vectors, the query representation and the document representation. You can do a dot product of these representations to form a single scalar valued feature which represents how close this document is to this query. Or you could do a Hadamard product where it's basically an element-wise product of the document and the query. Or you can just concatenate them and pass it through a neural network to get some sort of a score. Multiple different ways in which you can take the query representation from BERT and the document representation from BERT to get what we're calling deep features, which are cross features between the query and the document. So in this slide, these blue rectangle over here with multiple squares, each square is a real valued, is a scalar in this vector of, blue, in this blue vector. And we think the way we have done this at LinkedIn is to take a dot product between the query and a document field to produce 1 scalar. So the first square might be the dot product between the query and the first field of this document, D1. The second square may be the dot product between the query and the second field of the document, D1. And the third would be the third field of document D1 and the query's dot product. But you could form it, like I said, with a Hadamard product or other ways as well. So this deep features are computed using BERT to process the query and the document, and they result in some feature which tells us how close this document is to this query. The wide features are features that we have anyway. These are features having to do with what is the query about, what is the document. These are traditional features that we use. And then we pass this through a hidden layer to get a document query score, a score which gives us a match between the query and the document. And then we want to rank the document according to these scores. So we use a learning to rank loss as opposed to a classification loss, like a cross entropy loss. We don't use cross entropy loss, we use the learning to rank loss, which basically all it cares about is that the document that was clicked by the user in training. So in the training set, we will have a bunch of documents, or a few of which were clicked. And we want the document that was clicked to have a higher score than the documents that were not clicked. And that is what the learning to rank loss does. And we train this entire neural network using this learning to rank function. And that's how we do, and remember the BERT model is sitting over here. And therefore we are doing this back propagation of this loss through this entire network where the BERT model is shared across Q, D1, and D2, and Dn. And so we learn the parameters of BERT along with the hidden layers that we've shown over here. And this is the fine tuning that we do for document ranking. Okay, so now how do we use it? So turns out that we can pre-train BERT. We can actually just use Google's pre-trained BERT, which they released, or we can do pre-training ourselves. And the reason we might want to do pre-training ourselves is because if you take the world's language, which is a whole bunch of text about all different sort of domains, and you learn language very well by doing that. But if all you're interested in is to predict if a query is a people search query or a job search query, then maybe we don't care about legal documents, about Wikipedia and things like that. Maybe we only care about data that looks similar to queries. So we found that by pre-training BERT, using LinkedIn's own data, as opposed to using the Google BERT, we got better results. In particular, we used LinkedIn's domain of language. That is queries, member profiles, job descriptions, ads, and so forth. All the text we find in LinkedIn's domain, we used that to pre-train BERT. And we turned out that the corpus was about the same size of Google's, 2.9 billion words instead of 3.3 billion words. We trained a smaller model, a 6-layer model with 512 dimensional hidden layers, so 512 dimensional embeddings, as opposed to a 12-layer, 768 dimensional embedding that Google did. Our model, which we call LeBERT, because it's LinkedIn BERT, LI for LinkedIn, and that's trained on our own data, is 34 million parameters versus 110 million parameters for Google's BERT. Okay. The difference between LeBERT and BERT is simply the data that we use to train it. We've used this for this Help Center document ranking task. So in the Help Center task, basically you go to www.linkedin.com/help. You can type in a query such as how to edit my profile. And we want to return documents that tell you how to edit your profile. We have several thousand documents here, so this is not a huge task, and we can actually pre-compute our BERT representation for all these documents, which is why we used a BERT for this particular ranking task. We don't currently use BERT for other ranking tasks, but we are working on doing that. Now, how do we do the Help Center ranking task? Each of the document is comprised of a document title and an example question. So when these documents are written, we also write an example question for the document. And we also have the document title itself. These are the fields we process as far as the document is concerned using LeBERT. And we also process the query itself, as I said before. The deep features are the dot product, like I described before, between the query and the LeBERT embeddings for the document. The wide features are the dot product between the query and document TF-IDF vocabulary vectors. So this was the wide features that were just the features that we already had. In terms of training data, we had 240,000 queries, each of these queries with 10 results, one of which was clicked. And we used that to train to fine-tune our BERT model using the learning to rank approach that I showed you before. Now, during training, we are monitoring precision at 1, which is simply the fraction of documents that were ranked at position 1 by our model that also received a click in our testing data, right? So this is the data that we had collected beforehand to train our model. Part of it we used as testing, and precision at 1 was what we used to monitor whether the model was doing well or not. We have a baseline CNN model, and at LinkedIn, we don't give out actual absolute numbers in terms of our performance. We only talk about the improvements that a model gives over the previous model. So our baseline is a CNN model instead of a BERT model. The Google BERT base model gave a 2.65% improvement in precision at 1, but the LinkedIn 6-layer BERT model, which is 1/3 the size of the Google model, gave a 3.56% improvement over the CNN model. So it's significantly better than Google BERT and significantly smaller as well. And these are our 2 online metrics. When we ramp this model online, we are measuring 2 online things. One is called the happy path rate, which is the fraction of users who searched and clicked on one of these documents that were returned and did not return to the search center again, to the help center again that day. And search CTR is simply the fraction of searches that received a click by the user. And you can see that both of these metrics are significantly improved using the LeBERT model as compared to the CNN baseline. The second use case is query intent. Now, each query at LinkedIn can be classified into one of 7 categories: people, company, job, content, group, school, and learning. And the way we use this is when we show you results. So here is an example of person typing in computer vision engineer, and BERT, our query intent model, thinks that this is a job query. And so it shows a bunch of job recommendations on the top. In the primary search results are job results over here. And the secondary search results are people results, because the second most likely class for this query was people search. So that's how we use this query intent classification. We use the output of query intent classification to decide which will be the primary results and the secondary results. So query intent classification works like this. The input query is processed through BERT to produce a CLS embedding for the input sentence, right? That is our deep feature. And our wide features, which are the traditional features, are simply features about the query itself. For example, does this query contain a first name, last name? Does this query contain a company entity? And also, we are using member features, because the same exact query, like Google search engineer, right, typed by me or you, might mean we are looking for a job. That we are looking for a job as a Google search engineer. However, if a recruiter were to type Google search engineer, they are probably looking for people who are Google search engineers. And so that's a people search. So depending upon who is typing the same exact query, we might need to show people results or job results. And so we also have member features that are used. And these member features are features which are footprint features like, is this member, does he have a high job seeker intent at this time? Is this member an entrepreneur? Is this member likely to connect with a salesperson? We have models that predict these things, which become features for the member. And also historical features such as, did this member issue job searches, federated searches, engage with jobs in the past, and so forth. So these would be the traditional features that we have already used. And we add on top of this, the BERT features that we get from BERT. Okay, now during training of this model, we used query intent accuracy to determine if we were doing well or not. Again, we had a CNN baseline. The Google BERT base model gave a 2.89% improvement in accuracy, and the 6-layer BERT model gave us a 3.28% increase in accuracy over the CNN. Again, a statistically significant improvement. When we ramp this online, again, we see improvements across the board in our 3 different online metrics that we care about. The first is simply the click-through rate at 5, which is the fraction of results in the first 5 positions that receive a click in online. First order actions are actions that we really care about, because remember, LinkedIn, this is a professional site where we're trying to connect people to other people and other jobs. And so the first order action are searches for which a member actually connected with another person, messaged another person, or applied for a job. So if a person actually did this at the end of his typing the query, then we think that whatever we did to the model, in this case, adding this query intent model, did a good job. And the third one is satisfied clicks, which includes the first order actions, but also includes searches where the member had a greater than 5-second dwell time on the search result. So this is a superset of first order actions. And we see here a statistically significant improvement across all these online metrics. So basically, we found BERT to give us wins for both ranking tasks. It was a smallish ranking task. We are now working on actually expanding that to other ranking tasks, and also in this query intent classification task as well. So with that, I come to the end of my talk. This is the summary slide. We talked about how natural language processing is used for search and recommendation tasks. At LinkedIn, we actually use other deep neural networks as well. For example, we use an encoder-decoder model, attention-based model, to do query suggestion. I didn't describe that, but I told you we do this. So that's another place where we use deep neural networks. We also use it for query completion and for query tagging as well, in addition to the BERT examples that I gave you. We found that from a BERT perspective, it works very well, but it's a good idea to pre-train BERT on the domain-specific data. Rather than using Google's BERT or a BERT model that has been trained on gobs of data outside of LinkedIn, we found it made sense to pre-train BERT using LinkedIn's data. This results in a significantly smaller model that actually gives better results. And finally, we were able to show that BERT actually gave us significant online metrics gains in 2 different tasks that I described here in this talk. So with that, I'll stop. If you have any other questions, I'd be happy to take them.